What up, what up, what up? Section 7.2, volume by disk. This is the disk method. We're going to find the volume of a solid revolution using the disk method. Basically, what we're going to do is, last section we did cross-sectionals, different shapes, squares and whatever. Those aren't the most accurate because usually the figure is going to be curved, and if we have to use some sort of non-circular method or whatever, like squares and rectangles and triangles, then we're not going to get the most accurate representation of that volume. But in this case, what we're going to do is we're going to create a three-dimensional region by rotating the function around a line, which is what obviously a volume is, right? 3 dimensions. The rotation creates circular cross-sections that combine to create the volume. So the resulting solid is called a solid of revolution. And what we're going to revolve it around is what's called the axis of revolution. Okay, each of this circle's areas are going to be a equals pi r squared. That's something you got to know. Where r is the distance from the function to the axis of revolution. Most of the time, well, some of the time, I guess not most of the time, the axis of revolution is going to be one of the axes. So either the x-axis or that y-axis. Sometimes, which in some of the problems down below, the axis of revolution might be like y equals -1 or x equals 4 or whatever, and we have to understand that. And so here's my circle over here, all right, where I can see that I have the radius here. The width is the width of each circle. And those widths of each circle are actually going to be as small as possible, because then that gives us the largest amount of circles in the function that creates the most accurate area. Here is basically your function. Okay, you have your function down here, and we're rotating it about that axis of revolution, which creates this three-dimensional figure. And we can see that these are my kind of disks here to creating those disks, different colors because I'm awesome here. And then if you just kind of manipulate that out a little bit and you want to go and make smaller and smaller and smaller and smaller discs, this is what you're going to get. You're going to get to some kind of nice little cone, or on a lampshade, or whatever the heck this figure is. I don't know. Anyway, the disk method, there's two different ways you can do this. One's called horizontal and one's called vertical. And we talked about this in the last section with horizontal rectangles or vertical rectangles. It's very similar to what we did in that last section there. And so the horizontal axis here is going to be the volume is going to be equal to pi times the integral from a to b of r squared dx. We're going to fill in the r to be some x's. And what we're ultimately doing is we're going to say, this is from a to b, and our circles are going to be kind of like, our discs are going to be like in this range. They're going to be vertical. Okay, our discs are going to be vertical. And that right there is your height of r. Because technically this function is going to kind of come down here, and this piece is going to come down here, and that's going to create our solid of revolution. Okay. Vertical axis of revolution, it's going to be volume is equal to the pi times the integral from c to d of r squared dy. And in this case, this is from c to d up here, and our rectangles are going to be horizontal or perpendicular to the y-axis. Okay, and again, this figure is going to come down here, and then that's going to create our solid of revolution. Okay, let's get to some examples here. Let's do it. All right, fantastic. Example, using a disk method using the x-axis. Okay, find the volume of the solid formed by revolving the region bounded by this graph, and the x-axis from 0 to pi about that x-axis. So how do we kind of go about doing that? Well, we got to think about what this graph is going to look like. So real quick, the graph is going to be from 0 to pi, okay, 0 to pi, and the graph is going to look something like this. That not like flat, but it is what it is, where this piece here is going to be revolved around, okay, so it's going to look like a ball almost. It's going to look like a ball, all right? And what's our radius? Well, our radius is this function, okay, this function, because that's the top function. Basically what I'm doing in order to find my radius is we're going to take the top function, whatever the top is, minus the axis of revolution. Okay, minus the axis of revolution. So in this case, it would be the square root of sine x minus 0, right? Because that's x equals 0 right there, the x-axis, or y equals 0, sorry. And this is then my radius right there. So the volume is equal to pi times the integral from 0 to pi of the square root of sine x dx. Okay, I'm sorry, it's sine x square root of sine x squared dx, because it's r squared is the radius, right? So then this is going to be the volume is equal to pi times the integral from 0 to pi of sine x dx, right? The integral of that is negative cosine, and then you can evaluate that, and you're going to get about 2 pi. About 2 pi. Okay, so the volume of that ball, because it's going to be a ball, because it's going to kind of come down here, and then this is all going to be filled in. It's going to look like a ball. Fantastic, a ball. Next one, using the disk method for the y-axis. So in this function, we have x squared plus 1. So because we're going from 1 to 5, okay, the function technically is going to be x squared plus 1, so we know it's going to look like this. All right, we are going to go from 1 to 5. Oh, on the y-axis. Ooh. On the y-axis. Sorry. So this is 1, and then we'll say up here is 5 just for the sake of the graph. And this is going to be revolving, okay? So what we want to do is we want to find the area from 1 to 5. So we want to find basically all of this area in there. And we want horizontal rectangles in this case, because we're going about the y-axis. So we're rotating the function, and it's going to look like this. So it's going to look like an awesome kind of cone here, or like a tuba or something. It's kind of hard to see, but you guys catch hopefully my awesome graphs going on. And so in this case, again, we want to find the radius, but the radius is the graph minus the axis of revolution, which is 0. So the radius is just x squared plus 1. But this is y equals x squared plus 1. This would be great if we're going to finding the area down here. Okay, down here. But we're not, so we got to convert this. So I got to say, okay, it's y minus 1 equals x squared, and thus y minus 1 square rooted is equal to x. So that's the function. Because I'm getting horizontal rectangles, and I'm taking it with respect to y, I need the function to have y in it. I can't have y equals, I got to have x equals. So you got to remember that. So the volume is equal to pi times the integral from 1 to 5 of the square root of y minus 1 squared dy, which is equal to pi times the radius from the integral from 1 to 5 of y minus 1 dy. You can integrate that, right? That's y squared over 2 minus y from 1 to 5. All of that's being multiplied by pi, and you get around 8 pi. Okay, you get around 8 pi. So that's not too bad. Those first two are not bad at all. These next couple, if you've not done this last year, it might be a little bit more cumbersome. In this case, I want to take this function, f of x equals 2 minus x squared, and the line gx equals 1, about the line y equals positive 1. Okay, y equals positive 1. So what does this mean? Well, what it means is this. We have our graph. We're going to go like this. Okay, so we're going to go from, well, I'll tell you what we're going to go from here in a little bit. We'll figure that out. But this line, g of x equals 1, is a line that goes like this. Okay, that's y equals 1. All right, and this function, 2 minus x squared, is going to look like this. Okay, 2 minus x squared. And where it intersects this line, I could actually solve that. 2 minus x squared equals 1. And I get x squared equals 1. So x squared is equal, or I'm sorry, x is equal to plus minus 1. So this is going to intersect at -1 and +1. That's where they intersect. Okay, this is our x-axis. This is our y-axis. This is g of x equals 1. Okay, and this is the function f of x here. And what I want to do is I'm revolving it around the line y equals 1, which is the line that I have drawn here already. Okay, this line here. And how do I do this? Well, I got to find the radius of this here. And if I just say that the radius is 2 minus x squared, which is what it was in the first couple problems, I am basically taking this circle, or half circle, and I'm finding the area all the way down to the x-axis. And I don't want to do that because that's not what I'm doing. I want to take this, and instead of rotating it around the x-axis, like this ball would then be over here, and you would have some crazy kind of oblong-shaped figure. But I don't want to do that. I want to rotate it around the y equals 1 line, so the ball is going to kind of come look like that. And what I have to do is I have to subtract the axis of symmetry. So I have to subtract that axis of symmetry. So that's the radius. So I get 1 minus x squared. So that's the radius. Okay, you always want to subtract. This is the axis of symmetry, or the axis of revolution. We'll go axis of revolution, sorry. Okay, and so I get the radius is 1 minus x squared. Then I can use my volume formula from pi times integral from -1 to 1 of 1 minus x squared squared dx. What I would do here is I would probably just multiply it all out. So you'd get 1 minus 2x plus x squared, and all of that is going to be dx. And then you can integrate that, and you're going to get about 1.0667 pi, or something like that, rounded by, it's 1.06 repeated, okay, but something similar to this. So you're going to get approximated as this value. Okay, let's go on to the next one. We got 2 more to go. I'm kidding, 3 more to go. I can't count. I just teach math. I'm just kidding. Find the volume of the solid formed by revolving the region around this, y equals 3, x equals -1, and about that line, x equals -1. What does this look like? This is where you got to understand what graphs and stuff like that happen, okay? You can't just plug it in, I guess. I mean, you can do some like derivative calculations and things to find out where it's increasing, decreasing and things, but do you really want to do that? Not really. So we have the line x equals -1, so this we'll say is -1, x equals -1, okay? We have the line y equals 3, so we'll say this is y equals 3 up here. And the function, if I plugged in -1 to this function, I actually get 0. So the function is actually going to, remember what a square root function looks like, so this is kind of what a square root function looks like, okay? And I want to find the volume of the solid formed by revolving the region bounded by all of those 3 things. So I'm finding this region in here, okay, about the line x equals -1. So what does that mean? What type of rectangle am I going to use, or a circular disc? Because I'm revolving it around the x equals -1, I'm actually going to create, let me see if I can get a different color in here. I'm actually going to create a horizontal rectangle. So I got to take this function, y equals square root of x plus 1, and solve it for x. So that's going to be x equals y squared minus 1. Okay, x equals y squared minus 1. But I'm revolving it around the line x equals -1. So I have to subtract, so the radius is equal to y squared minus 1 minus the line that I'm revolving it around. So it's y squared, and then that just cancels, right? So it's just y squared. So that makes my life a lot easier. So now I want to take the integral. Okay, the volume is equal to pi times the integral from where to where. Well, it looks as though this is 0, so this is going to be 0, and this is going to be positive 3, right? Because that's our y equals 3 line, so 0 to 3 of the radius, y squared squared dy, which is y to the 4th, which is y to the 5th over 5 when I integrate it, from 0 to 3. All of this is by pi. So I end up with around 48.6 pi, give or take. It might be more decimals, but that's what I wrote down, so that's about what you get. All right, you got 2 more to go, and this is a awesome length of a video. All right, the second to last one, I guess. Find the volume of a solid formed by revolving the region around y equals x squared, the x-axis, and x equals 2 about the line x equals 2. So first, let's kind of get a graph down. So y equals x squared is going to look like a generic parabola. The x-axis, great, and x equals 2. So x equals 2, we'll say it comes right there. That's fine. That doesn't really matter. But if x is equal to 2, then y is equal to 4, right? So this is the point 2 comma 4, and this is 0, 0. Fantastic. And about that line, x equals 2. So what do I got to do here? Well, because I'm going about the x equals 2 line, that means this area over here is going to be horizontal disks. So I'm going to need to take the function and solve it for y. I'm sorry, solve it for x. So x equals the square root of y. All right. So then what I gotta do is what I gotta do. Oh, it's like a rap song or something like that. I don't even know, like hip hop. Yo yo yo. I have to find the radius, which is I take the function and I minus it over the axis. I'm kidding. Let me back up 1 second. 1 segundo. Okay, here we go. This is why this one's a little complicated. Because the axis of revolution is the furthest thing right. Okay, this blue line. This is the furthest thing right. If I look from the y-axis, this blue line is the furthest thing right. So when I find the radius, I have to take whatever's the furthest right and minus whatever I have to subtract. So in this case, it's the line that I'm subtracting. Okay, in all of the other problems, all right, I was subtracting it from the line because it was we're going from right to left here or left to right. So I'm able to do that. Okay, because this line here is left. Okay, it's left of the function. I didn't have to do that there. This one here, because I was rotating it around the y-axis, so that means the function was to the right. So when I subtracted, I went right minus left. In this case, I want to go right minus left, so the actual line of revolution, the axis of revolution, is to the right. So I have to subtract that number first. So the radius is 2 minus y. So then the volume is equal to pi times the integral of 0 to 4, because we're on the y-axis, 0 to 4, I know it doesn't look great, but it is 4, times the radius, square root of y, squared dy. Okay? So you can probably, I would say, you should be able to use your calculator right now and do this. If you wanted to multiply this out, you should get 4 minus 4 square root of y plus y. Okay? And you can very easily integrate that without a calculator. But if you wanted to use, what is it, Math 9 on your TI, Math 9 on your TI to find out what you get, and you should get about 2.667 pi. And you got to multiply all of that by pi, right? The antiderivative there. Okay, let's do the last one, and then let's call it a day. Let's call it a night, because it's only 8:17. It's a good night right now. Find the volume of the solid formed by revolving the region bounded by y equals x squared, y equals 4, and the y-axis about the line y equals 4. So again, we have our x squared parabola, which is going to go something like that garbage. Y equals 4, so we'll call y equals 4 up here. The y-axis, okay, so y-axis is right there, and that line. So we're finding this area right in here. And because I'm going about the line y equals 4, I'm finding vertical disks. Okay, vertical. So I can leave my function in this form, y equals x squared. Okay, but in this case, I can't go x squared minus the axis of revolution. All right, I can't go x squared minus the axis of revolution. I have to go from the top down. So I can go 4 minus x squared. This is my actual radius. Now, here's something that you got to understand. When I square this, or square this, I get the same thing. Okay, I get the same exact thing. So even if you did it backwards, okay, even if you did x squared minus 4, and you square this because of the radius, right, pi r squared, you're still going to get what? X to the 4th minus 8x squared plus 16. Well, guess what? Even if you did it the correct way, which is over here, star, 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 you're still going to get 16 minus 8x squared plus x to the 4. You're going to get the same thing. All right? It's going to get the same thing. So regardless of you doing it, because you're squaring it, it is okay to do it the backwards way. Now, is it the proper mathematical? No. But if you get in a jam and you forget kind of how to do it, that is okay. All right? Now, let's finish this up here. So, that's our radius. That's our radius. So, we got volume is equal to the pi times the integral from 0. And if it's y equals 4, then x has got to be 2, right? X has got to be 2. So, from 0 to 2 of the radius, which is 4 minus x squared dx. And again, calculator, you can do it longhand, but you get about 17.06 repeating. Okay, pi. Fantastic. It's another long video. I'm sorry, but should go pretty fast if you actually did this last year. If you didn't, then you probably will spend a little bit more time on this. Have fun. On to the next section. Deuces.